We're in a part of the cave where we have some very large passages. This is the start of Gnome Passage, which is wide, and obviously it causes collapse in thinly or well-bedded limestone. You can see there a very extensive flat roof in the more massive beds, which form a large part of the roof here. Prior to this forming, you had what we call a phreatic rise or up movement of water into the roof. Even further up, we have the ultimate flat bed again of the Pendaring oolite. Beneath the flat roof, there is a funnel shape, like that, for the climbers who've been up there. And this is fairly common in the roof along Gnome Passage. They don't necessarily connect to the bedding chambers, but they are very similar in appearance, but on a smaller scale. Right, the presence of these phreatic features is an indication that the passages were formed under the water table. You get very intense erosion produced near the phreatic-vadose interface. An awful lot of chemistry goes on at these levels, which is just of the Tower River, the Proto-Tower River, which is at about this height. And that controls the position of the water table. Okay, we're in some very large passages here, which would normally extend in the north and westerly direction. They seem to have been truncated by a cutback of the surface as a result of a variety of causes, mostly scarp recession, or helped in many ways by some fairly static glaciation at this level. This is one of the major faults affecting this series. It identifies the fault plane, and the down throw on this side of the fault is 4.5 meters. It has clearly moved down the favourable beds that are conducive to cave development here, so that there's an apparent drop away to a lower level, but it's actually in the same beds as forms Gnome Passage. This is a fairly common feature in the cave at this level, where we have a fairly coarse-grained sand which is clearly deposited underwater. It's also a very late stage feature. The passage and the ledges were clearly in existence beforehand. The sand is fairly unconsolidated, and it's coarse, indicating that it probably dropped out of water at a fairly early invasion of the sandy material in a slurry of water. As we get further into the cave, these become less and less frequent, so that a similar ledge further down is fairly free of this type of deposit. As you can see, there is a general dip from right to left at about 10 to 15 degrees, and you can then see that there is a sub-horizontal dissolution groove cutting across the bedding. They form at the water surface. They take many hundreds, maybe thousands of years to develop. Surface water reacted with the carbon dioxide in the cave air at the time and produced near-surface enhanced corrosion. The flow of the water was fairly gentle, as can be seen from the frequency of the fluting. It indicates that the passage was largely in existence, and it would be consistent again with post-production flooding at some stage, though this is hard to be too certain about that. This roof shows several interesting features. The primary dissolution tube is in the roof, and obviously there has been collapse up to a flat surface again, but with remnants of the phreatic roof meander still in existence. As the passage increases in size, so we get further collapse with another fairly stable roof. This is eroded by anastomosing dissolution tubes, which are probably a result of distributaries from the main flow of water in the main passage. As we go further and further down, so the passage gets wider and wider, and then there is further collapse to a fairly stable bed. A bed in many ways can be regarded as an irregular lens. If it is deposited underwater, then clearly as you come towards the shore, then a bed becomes thinner and thinner. And again, as it goes in the opposite direction, it may change in character. This is a fine example of what we call wedge bedding, where you can see that there's been some washout of part of the beds and its replacement with an infill.